Welcome back to our session number 14 on beams. This is the third and final portion. We've discussed in the last portion how to derive the shear formula, which is what relates the internal shear force or the derivative of the bending moment to a transverse shear stress. And we discussed how we have this quantity called Q in this equation, but we haven't gone into a whole lot of depth in terms of how to calculate it yet. And that is going to be the subject of our last portion here for session 14. So let's talk about how we've already kind of come up with this expression, okay, the first moment of area, and it's equal to this integral y dA prime, and it's equal to y bar prime. This is known as the centroid, okay, times the area prime, okay, and this calculation of centroid is something that you likely saw in statics. But the Q term, this big Q, is just the top portion, okay, of what you would have used to calculate the centroid, or what we would have used to calculate the centroid in the past, okay? So let's take a look at how you find the centroid using this equation. And this may be a review from previous courses, but it does kind of shed some light in terms of how the math relates to the geometry of a cross section that we might be studying. Here we have a profile, a cross-sectional profile of a rectangle. And I guess it's kind of squarish. Maybe I should have made it more rectangular. Nonetheless, it is going to have some area A prime, and we're defining a y coming up from this bottom side of it. The area A prime is simply the width times the height, as we see here. Now, as we've kind of done in the past when we were calculating second moments of area, we take a slice, and kind of a really thin slice, and we say that's got some thin height, and it has the width that goes along with the cross section. So we can define this dA prime, or the slice of the slice, or the slice of the profile, as T dy. So now we go back to the equation that we have for calculating out the centroid as y bar prime. Okay, and what is y bar prime going to tell us? It's going to tell us where, in terms of this y parameter, so only in the vertical direction, where is the centroid of the object of this area? Okay, and so what we do is we plug in the T dy, all right, for the dA prime, and we have y, all right, that's already in there, and we're going to go from 0 to h. Now, this is maybe a little bit different than what we have with the normal cross sections of beams, where you're kind of going up from the neutral axis. But here we're going to span the entire area, and that is similar to what you do when we have the opportunity to calculate a first moment of area in a region above the neutral axis. So that will become hopefully more clear as we discuss things further. But what's neat here, okay, is if we do the math, right, so we perform this integral, we substitute in the th for the a prime, we get that y bar prime is equal to half the height. Okay, so just kind of, this is not a proof, right? You do one, that makes sense, and you're like, okay, that's great. But this demonstrates some common sense with this equation, that the centroid is halfway up this rectangle. Okay, so that's where you would put the centroid, right in the middle, assuming that kind of this nothing odd is happening. I mean, if you're thinking about centroid or center of mass, right, and you have different density over a given area, then the centroid might move. But this centroid is only using the area only using the geometry here. Now, if we were to flip this system and think about taking vertical slices and say, hey, X is on this side, going from left to right, we would similarly see that X bar prime, right, just kind of doing this integral, but, oriented 90 degrees from what we did, we would see that X bar prime is equal to 1/2 t. And that's also intuitive. That's what makes sense. So we've used this version of q over a prime to be able to say, okay, this is how you calculate the centroid. And this is where the centroid would be. In our treatment of statics or mechanics here, what we're really interested in is the y component. Okay, so like you can imagine, we're interested in, okay, what's happening above the neutral axis in some given region, and that's what we derived, or that's this q is part of the derivation that we had in the last portion of this session for the shear formula. So here's the shear formula again. Okay, tau is equal to VQ over IT. Okay, V is the shear force on the slice. I is the second moment of an area, moment of inertia. Okay, so let's just, yes, you can use moment of inertia. Let's just say second moment of area here, okay, to be a little bit just more specific. But what is very important is that it's acting over the entire cross section. And y bar prime is the distance to the centroid of the area. All right, so that is an interesting quantity. See, remember when we were looking at calculating transverse shear, we are putting it at some, or we're interested in at some location y prime. And then we're looking at the stresses and the loading above that region, because that's what has to balance out the tau, or the tau dxb, if that's the width into the page. All right, so you can go back and look at that portion there. So what we really get interested in is this area, this a prime above y prime. Okay, this is confusing. It takes a little while to get a hang of this. And going even further, if we look at q, all right, and we say we want to figure out how to calculate q without doing that integral every single time, we can find the centroid of this green portion, all right, of this region above where the tau is, above where y prime is, and then multiply by the area of that region, okay, to get the first moment of area. Okay, so this is for us to be able to calculate the shear stress at a location that we specify with y prime. So y prime is something that we specify and can change. All right. And if you're interested in learning more, or getting more details, just take a look at Hibbler's book. All right. This comes from there, and it's chapter 7. Okay, and this is Mechanics of Materials, and I have a slightly older version, the 9th edition. Okay, so let's do an example with a rectangular cross section. And you're like, well, we kind of already did this. Yeah, we kind of did. We had a question at the end of the last portion and said, okay, here's the Q when you're interested in the shear stress at the neutral axis. But now we're going to say, let's take a look at some distance above the neutral axis. We're going to be interested in some and calculating what the transverse shear stress is at this y prime. Okay, now this red dot is not the location we're interested in calculating the transverse shear stress. This red dot is the location of the centroid of the a prime corresponding to the area above the y prime. Okay, are we confused yet? Most likely. Okay, well, let's stick with it. Stick with it. And if if you want to spend some time, it's, well, if to get a different person's perspective on this y prime, y bar prime, and a prime, check out Jeff Hansen's YouTube video on what the heck is Q, all right? And he kind of goes through it nicely. All right, so let's say we have some shear force V, okay? And this is dependent on X, right, along the beam. And we have our Q, our equation for Q, all right, that's the first moment of area. Let's calculate out y bar prime, okay? And actually, I guess this, see, another typo, right? There should be a little y bar prime there. Okay, so y bar prime is what we can describe as being the centroid, okay? The location of the centroid of this A prime. And where is it? Well, it's located halfway between the bottom of this and the top of this. Maybe I'll zoom in to make this a little bit easier, okay? So it's located halfway up here. So what does this mean? That means that I'm interested in figuring out where this centroid is relative to the neutral axis. And I know it's kind of halfway up in between this green line and that green line. So I have to go up y prime already. Okay, so that's what you see here. I'm going up y prime to that location. And then we need to know what is this distance from here to here, right? What's this extra little distance here? Oops, okay, it doesn't let me draw when I'm zoomed in. All right, but what is this little, like the distance of my hand, or this hand right here? What is that? Well, h over 2 describes this half thickness, right? So h over 2 minus y prime, all right, will give us this hand height, but I need half of that hand height. So h over 2 minus y prime divided by 2. Yes, I understand this is a little bit complicated, and we can then write that y bar prime is equal to y prime over 2 plus h over 4. Okay. What's the area? A prime? Well, we already figured out, we just discussed that h over 2 minus y prime is this height of the A prime, and the t is the width of the A prime. So we now know what A prime is. So Q can be calculated out by having a y bar prime times A prime. An expression for I, okay, sorry, not A, I is what we often call BH cubed over 12. That's the second moment of area. We calculated that out previously. And for the entire cross section, okay, so you can forget the A prime stuff, you can forget the Y prime stuff. If I go to a different Y prime, so if I'm at a different height along the profile, okay, if I'm at a different height, I does not change. I is dependent on what the cross-sectional profile, what the cross-sectional geometry is. So now we've got Q, we've got I, we know T is T, and we were given shear force V. We can substitute all these parameters into the shear formula, okay, into V quit, and this is the expression we get. We can do a little bit more algebra, and it's a pretty hefty expression. So if we're interested in calculating the transverse shear stress, some distance above the neutral axis, this is the expression that the general expression that we might use for rectangular cross section. Now, as we did in the question from the last portion, we were interested in what is the max shear stress at y prime equals 0, or at the neutral axis. And so that simplifies things a little bit. If we perform the appropriate substitutions and we do the algebra, we get that it's going to be 3/2 V times 1 over TH. Well, this is something we can write like this, and V over TH is what? Or TH is what? That's the area. Okay, TH is the area. V is a shear force, internal shear force, and I'm like, wait, V over A, I've seen that before. That's the expression for the average shear stress. Okay, so it's typically pretty straightforward to calculate an average shear stress. You know what the area is, and you know what the shear force is. Once you've done those two steps. So now, if you're ever interested in the maximum shear stress at the neutral axis for rectangular cross section, boom, you just type in 3/2 tau av, and you save yourself some time. Let's talk about some different types of shapes, their moment of area, and shear stress. Okay, so what is the maximum shear stress for the following shapes? And there's quite a bit of algebra that I'll try to go through pretty quickly here, to be able to kind of not take too much of your time, but all this algebra is going to be available, or is available, on the instructional slides, and you can go through it, at your leisure, as they say. So the three cross sections that are going to be of interest here are a circular cross section, a rectangular one, and a hollow one. We actually already did this one. So rectangle, done. We know it's 3/2 times tau average. Okay, and that's something that maybe you want to write on your your note sheet for the next exam. And these other ones we are going to derive, okay, for the circular cross section and for the hollow cross section. So I'll try to go kind of quickly. We have tau is equal to VQ over IT. We know that we can calculate a Q by using the centroid of the particular A prime that is of interest, or we can perform it with integration. The cross section, right, of a circle that's of interest, if we're looking at what's happening at the neutral axis, is going to be a semicircle or a half circle. In that case, we probably are. I mean, if you know where the centroid is for a semicircle, a half circle, then fine, you can use that. Or we can say that we're going to perform this integral and calculate it out. All right. So we have our y, which is equal to r sine theta, and we then perform this integration, and we get that q is going to be 2/3 r cubed. Now, let's keep going. We've done this integral, and we want to say, okay, what is the y bar prime? All right, so we already calculated q, but for kicks, right, we can say, okay, if we ever want to know where the centroid is above the midpoint of a semicircle, it's going to be 4r over 3 pi. Calculating out the maximum shear stress, we have it being equal to VQ over IT. We're going to plug in y prime is equal to 0. We know that the second moment of area for a circle is pi over 4, r to the 4th. And we can now plug these parameters into our shear formula, and we get that we have 4/3 times v times 1 over pi r squared, and pi r squared is the area of the circle. So once again, if we have the internal shear force and we have the area of a circle, which is pi r squared, we just said that, then we can figure out what the average shear stress is. And the maximum transverse shear stress for a circular cross section is 4/3 times the average shear stress. Okay, so this is another potentially useful formula to keep in mind, and maybe write on a formula sheet somewhere. So to kind of recap this derivation, we can say that for a circular cross section, there's going to be a profile of transverse shear stress, and the maximum happens at the neutral axis and is 4/3 times the average shear stress. Okay, let's now look back at the rectangular cross section and just write out the equation that we have here. Let's look at we did that one with the circular cross section, okay, and the equation that we have here. Okay. And then also, we're not going to derive it, but we'll throw out the thin-walled hollowed cylinder. So this is an approximation that might be useful, and it is that we can approximate that the maximum shear stress, again, at the neutral axis is going to be approximately. This should really be an approximate expression. Whoops. Right here. That's even worse. We'll just write it like this. T max is approximately 2 times the average shear stress. Okay, which section have we not done yet? Well, the hollow rectangular cross section. Okay. Now, this rectangular section, okay, is it's a little bit tricky, okay, and we still know that the shear force is going to be a maximum at y prime equals 0, okay, and we still want to figure out a q, and we are wanting to kind of think about our geometry in terms of parameters defined away from the neutral axis. So here we're going to say we're going up to some h over 2 minus w, right, to the bottom here. And then we're going to go from this h over 2 minus w to the top. Okay, and they have different cross sections, right? They have different t's. So now what we can write out is that we have a q is equal to this integral plus this integral. Okay? These are dA primes, which are different. Okay, 2w dy describes this profile, whereas the b describes the profile, okay, the width of the profile, I should say, above this h over 2 minus w. We can continue and perform more integration here, and we get another expression and yet another expression for q when we do the algebra. And that is essentially, yeah. So we're essentially done with the hard part with this problem. We have q, and we can plug that into v-quit. So if we have an internal shear force, we have a q, and we have an I and a t. Okay, we can go ahead and make the calculation for the shear stress. Another way to look at this problem is to use something akin to the parallel axis theorem, okay, but we use that for moments of second moments of area, okay, but we can do something similar where we are going to remove, okay, a region. So we have a region, and we have the region that we're going to hollow out. And what's nice is that we can subtract, okay, or these different q's, they sum up with each other. All right. So once again, we'll go kind of quickly here, but we see that y1, so the y1, that's for this region here, bar prime, can be defined by h over 4, and a1 prime can be described as bh over 2, and we can get similar parameters or do similar calculations for this region that we're removing. And then we can calculate overall Q. Right? The overall Q is going to be the, the Q1 minus the Q2, which we're calculating here. And we get an expression for Q again, which again we can plug into the shear formula. A little more. Okay. All right. So the shear stress, okay, that's also again a typo, will be a maximum at y prime equals 0. We have the V quit. We have our shear force. We have Q. We have T at y prime equals 0. That's 2W. Okay. And if we want to figure out I, well, we go back to what we know from our previous session, right? We have a BH cubed over 12 for a big region, and then we have this inner part, and it shares the same neutral axis. So we can hollow that out and subtract kindly from the large region to determine what the quantity is for the second moment of area. And with all these parameters, we can then figure out what the transverse shear stress is. This is not a simple undertaking, okay? And it requires some careful accounting, essentially, keep track of these different quantities. And we're doing this with variables, right? So when we have actual numbers, we have to also make sure we're keeping track of the units. Okay, so here's a question that's similar to the one that we asked at the end of the first portion of this session, which had to do with, okay, how does the average shear stress compare to half of the maximum bending stress? And now we're not going to do half. We could have done half, okay, but we're going to ask ourselves the question of how does the maximum bending stress compare to the maximum shear stress? And we're going to look at a situation where we have essentially a double shear configuration, or we have 3-point bending if we're looking at a beam. Okay, so I guess it becomes double shear, right, as the length gets reduced. So when we're looking at which one dominates, what we're really asking is, or we're looking at when they're equal to each other. This is the length of this beam, okay, the length of this beam when these are equal. So the shear force diagram looks like so, and the bending moment diagram looks like so, and we've put this out before. So what's the bending stress? The bending stress, well, that's going to be the negative my over I, and we can use our expression for m being a max at PL over 4, okay, or a max of PL over 4 at L over 2. And we can plug it into the flexure formula and write out the following. We have sigma max is equal to this quantity, and this is equal to 3/2 PL over BH squared. The shear stress can be written out as simply tau max is equal to 3/2 times tau average, okay, because we calculated it out. What is the shear force? Well, the shear force is max is P over 2, and the area is BH. So we can write that expression out like we see here. And this becomes 3/4 P over BH. All right. So when are these two quantities equal to each other? Well, we plug in, or we plug in these two expressions into the equality we've set up. We do a little bit of algebra, and we get that the maximum shear stress will equal the maximum, or the maximum bending stress will equal the maximum shear stress when L is equal to 1/2 H. Okay, this is a different quantity than we got last time, and last time we were looking at half of the maximum bending stress, and we were comparing it to the average shear stress, but it is, again, a very small length of a beam where the bending stress and the maximum shear stress are the same. 1/2 H, we're saying shrink your length of your beam down to half its thickness, and that's when shear stress, and if you go beyond that, that's when shear stress will begin to dominate. Okay. So when L is greater than 1/2 H, sigma dominates. When L is less than 1/2 H, tau dominates. So when we discuss deflection, and if you already saw the efficient engineer in one of the videos that we posted of theirs, okay, that shear stress actually doesn't usually contribute a great deal to the deflection of the beam. Okay? And often when we're concerned about is the beam going to break, okay, we're looking at the bending stress instead. Okay, and to conclude this session, all right, we have a problem, all right, with this overhanging cantilever beam, similar to what we had from session 13. Okay, but now we're going to ask for the neutral, or what the maximum transverse shear stress is at this specified location. Okay, a distance from the right. Okay, so we're going from the right of the beam, a distance d. To conclude, what have we, what are some of the things that we've covered in this session? It's been pretty deep. I hope that we now have an augmented understanding for how shear stress would be present in very short beams in terms of single shear and double shear. Hopefully, we also have some intuition now and tools for calculating what the transverse shear stress would be as a function of the internal shear force. Okay. And we've also spent quite a bit of effort to describe how the first moment of area is calculated and how that first moment of area affects the transverse shear stress for systems. And so this is kind of one of the diagrams that you might want to write out similarly, that describes what y prime is. That's the distance to the point of interest. The centroid is not the point of interest, okay, but it is the centroid of the area A prime associated with the bottom of where y prime goes up to, where the actual shear stress that we're interested in evaluating resides. Okay, well, thank you for your time, and I look forward to the next time that we get to chat.